Good afternoon, and welcome once again to our weekly security seminar series. This week, we're privileged to have another distinguished speaker from Purdue University. Professor Ed Delp of Electrical and Computer Engineering has been working for a long time in the area of watermarking and digital protection of intellectual property. And we're pleased that today he'll be talking to us and giving us an introduction to image and video watermarking technology. Thank you.
Well, thanks, Gene. And I'd like to thank Gene for inviting me. I think what I'd like to do is just, Steve, we can just go ahead and go to the first slide. So what we have here is I'm going to give a little talk on the introduction to image and video watermarking. And I guess we'll take some questions. I don't object to taking questions as we go along. I think that's probably possible. My web page, my URL there for my web page is where you can go to find out more information. For those of you maybe you can't read it out there in TV land, if you just want to go to www.purdue.edu and then click on academics and then click on engineering, click on electrical and computer engineering, click on faculty, and then you'll see my name and you can click there and go from there. So it's about 5 or 6 clicks if you can't remember how to get there directly. And you'll find lots of information about what we're doing in the area of multimedia security and also copies of some of our papers. So what I want to talk about is this a little overview of digital communication systems. And this block diagram is pretty interesting because this block diagram is essentially 50 years old. This is essentially the block diagram that Claude Shannon proposed in his seminal papers called the Mathematical Theory of Communications that were published in 1949 in the Bell System Technical Journal. So as a side note, that also was the same year that I was born, to give you an idea how old I am. And Shannon essentially did 3 things. He published seminal work on source coding, which is essentially what we call data compression. He also published seminal work on channel coding, such as error control codes. And he also published the seminal papers on cryptography in the 50s. He published a paper called The Mathematics of Secrecy Systems, where he essentially talked about some of the, he brought cryptography into the area of communications. If you look at Shannon's papers, he'll show you this type of block diagram. And if we look here, I guess this pointer is okay. Can you see the pointer okay? Okay, so you start off with some sort of digital communication source. You usually have a source encoder, a data compression step. You have an encryption step. You have a channel coder. The point of the channel coder is to essentially insert redundancy back into the stream so you can use that once it goes through the channel because there will be errors introduced in the channel. The decoder then should be able to correct those errors. You'll see the decryption step, the source decoder, and then the user. Now what's important here is notice these 2 blocks. Okay, It is absolutely theoretically correct that you want to do encryption after you do source encoding. And the reason why you want to do that is the source encoder, one of the things the source encoder is supposed to do is remove redundancy from the signal. So by removing redundancy from the signal, it allows you to essentially, well, you will have less of a path to attack the encryption system. Now, I just said that, but I will tell you that most, if not all, watermarking technologies reverse these 2 boxes. And so you can say that it's theoretically bad, and we are actually looking at problems like that here at Purdue. But generally what happens is the watermarking, which you can think is in a form of encryption, it's not a very strong form of encryption, but what happens is watermarking is usually done before the source encoding, and there still could be encryption in the step. Okay, if you look at multimedia applications, the types of things people are trying to talk about, and Gene certainly talked a lot about this at his last presentation. You know, people are interested in things like privacy and things like forgery detection and copy protection. You know, things like proof of delivery, proof of purchase, intruder detection, network security, and also being anonymous. And it's important that the security system that you introduce really should not be noticed by the user if possible. It'd be nice if the user wouldn't have to worry about this. And there's lots of other bullets on here. I mean, you know, the talk that was given last week by Gene had lots of other bullets on here. But, you know, these are some highlights. Now, for multimedia information, particularly for things like images, video, and audio, there is problems having to do with, let's say, if you use full encryption. I mean, you could encrypt, you could do full encryption, and there are applications I'll talk about where that that happens. You could also use a digest. In other words, you could hash the signal because you can't encrypt everything, perhaps. But there's a problem with how encryption works, does and does not work and complement the compression techniques, because all of these media signals are going to have to be compressed. Okay. There's also some issues about making the encryption technique fast enough. Now, right now, there are issues that you can do real-time encryption of video, but you sometimes get into some problems. For instance, uncompressed high-definition television has an uncompressed data rate of 2.5 gigabits per second. Okay? So if you want to do uncompressed high-definition television, you want to encrypt it, you're going to have to be able to go that fast to be able to do the encryption and decryption. Now, the types of tools that people, of course, use, and I'm sure you're very familiar with, would be encryption. Authentication, of course, is a form of encryption, and hashing and timestamping. Now, one of the things that I am a big fan of in multimedia applications, particularly for asserting ownership, is timestamping. And in many applications, to assert ownership, you might be better off doing timestamping. I'm talking about a cryptographically strong third-party escrow timestamp. You might be a lot better off doing timestamping than even doing watermarking. But you see these types of tools being used in multimedia systems now. And you're going to see more and more of this. And I'll talk a little bit about this later on when we talk about the Copy Protection Technical Working Group that's forming in Hollywood to look at protection of multimedia content produced by Hollywood. Now, there is a problem with, I mentioned that some of the cryptographic things are too slow, but you can use cryptographic approaches to do things like negotiate transactions, but what about the actual data? The problem is that you're overwhelmed. Whereas you can use cryptography very easily for things like email and stuff like that, you can easily be overwhelmed with images, video, and audio, particularly video. It's not unusual for even a compressed, 2-hour movie with reasonable compression is going to be about 1 gigabyte per hour. So if you want to have thousands of hours stored in of video stored somewhere, you might end up having to have many tens of 20s of terabytes of information. Now the problem is if you have to encrypt that and decrypt that every time you want to use it, you can get into some trouble. Of course, the other issue is that once you decrypt it, then the content is available. And this is a problem, particularly when people are going to be looking at the content or viewing it. Now, this idea of watermarking, which in the simplest sense, what you do is you insert a controlled amount of distortion into a multimedia element. And this is basically what watermarking is. It's a form of steganography, and I'll say something about that in a second. People are talking about, I'm familiar with work going on in watermarking, looking at audio, video, documents, including HTML documents, images, graphics, graphical models that say, like, for instance, that are used in MPEG-4, other types of graphics. And there's some work here in the computer science department where people are actually looking at watermarking programs as executable type code for doing some forensic type stuff. Although I'm going to concentrate in my talk on mainly images and video. I'll say some things at the end about audio, and if you want me to say some more about audio, I can mention that. Now, of course, there's this area of steganography, which really means covered writing. Essentially, it's data hiding. It's the idea of taking some data and hiding it in some other data in a way to conceal the very existence of the information. Now, it's been used a lot longer than actually cryptography. Some of the earlier papers on steganography predate a lot of the work that was done in cryptography. There's actually a lot of work going on in steganography, of which watermarking, I guess you could argue, is a special case. Okay. The idea being here, I'll talk about some of the research issues as we go on, but there's a lot of interesting research going on. Now let me talk to you about why the digital watermarking problem is important. So an owner places a digital image on the network server and they want to detect redistribution of altered versions. So what you might want to do, and it depends on your scenario, and in some of these cases this will work, in some cases maybe it won't. And by the way, at the end of the talk I'm going to talk to you about some that besides being a fan of watermarking and certainly devoting a lot of research in the last 4 years, our group here at Purdue is one of the leading groups in watermarking. I'm also a watermarking skeptic. So I'll tell you some of the skeptical things about watermarking. Even though I have 2.5 Ph.D. students sitting over there, there's a half a Ph.D. student sitting somewhere over there who are working on these problems. Is that you, Ray? Okay. Goals. So the goals of this thing is you'd like to verify the owner of a digital image, and it would be same for audio or video. You'd like to detect forgeries. You'd like to identify illegal copies. And you'd like to also perhaps prevent unauthorized distribution. This would be like the conditional access mode. Now, let me give you an example of why watermarking is important. This is a cover from the November 1993 issue of SPIE magazine. Now, SPIE magazine is a political satire magazine. I think it's still published. It's published here in the United States. And this was the cover of the November 1993 issue of SPIE magazine. Okay? Now, SPIE magazine has a reputation that every one of its covers consists of forged images. This is a forged image. Okay? Not only is it a forged image, it's extremely biting political commentary. So what is the political commentary? The actress here did not pose for this picture. This is the actress Daryl Hannah. Okay? When this was going on, Daryl Hannah was dating John F. Kennedy Jr. Okay, now John F. Kennedy Jr. unfortunately died this summer, but she was dating John F. Kennedy Jr. In November 1993 was 30 years to the month since John F. Kennedy Jr.'s father was assassinated. And what they did to Daryl Hannah is they stapled the same dress that Jackie Kennedy was wearing when John Kennedy was assassinated on her body. Okay? And if you don't believe me, there are pictures that are taken on November 22nd, 1993 in Dallas, Texas. These were taken hours before John Kennedy was assassinated. And you'll see that dress is very similar to the dress, if not identical to the dress that Daryl Hannah is wearing. Okay? Now, to say the least, this caused a lot of political stir. Okay? The Kennedy family was very upset. Daryl Hannah was very upset. Now, you could argue, well, you know, can you actually prove that this image has been forged? Well, if watermarking technology existed and it was used, and I'll give you some other examples, it would be very easy to prove that this is forged. Okay? Right now, there's a tremendous amount of effort going on because there's a lot of actresses that are finding nude pictures of themselves posted on the internet that they didn't pose for. Okay? In other words, they've been faked. And there's been actually a couple of lawsuits. Okay? So this is an example. By the way, I like to collect forged imagery. I have lots of them. Here's another example of an image that people are more interested in authentication. It is estimated there has probably been $200 million spent on trying to authenticate these two images, whether or not these images are real or not. These are the so-called, these are also related to the Kennedy assassination. I have two things relative to the Kennedy assassination. These are the pictures that are taken of Lee Harvey Oswald in the back of his home in Dallas, Texas. Okay? The rifle that he's holding on the left side, what he's also holding on the right side, is supposedly the rifle he used to kill John Kennedy. And the handgun that you can see that is on his hip was the handgun he used to kill, supposedly, and I'm saying supposedly, I really believe he did. He killed the Dallas police officer right after the assassination by the name of Tibbetts, I believe his name was. Okay, there was lots of speculation that that was not Lee Harvey Oswald's body. That was another head that was glued on his body. The other thing that was important, and you can't see here because the quality of my images I have is not very good, is in the left-hand image, Oswald is holding a newspaper, and it's actually a copy of the Dallas Daily Times or Sun Times. And it actually, in the actual photograph, you can read the date of the newspaper, which is also significant because it predates, it indicates Oswald owned these guns beforehand. I talked to the person, as a matter of fact, I know him quite well, the guy who served on the Warren Commission, and also a later commission was in the 1970s by Congress to authenticate these photographs. And he told me recently that he feels these photographs are authentic. But if this happened today, given modern digital technology to manipulate images, he doesn't think he could show that these images were authentic. Now, if these images were watermarked inside the camera, it would be very easy to show that they were tampered with. Okay? Because if you put a fragile watermark, I'll say a little bit more about that, you can see that the watermark has been changed, and then you would essentially not think the images were authentic. Okay? Here's another one. Okay? Didn't think you were going to hear about OJ today, did you? The image on the left, which is a cover of Newsweek magazine, is probably closer to what O.J. Simpson's booking photograph actually looked like. The one on the right is the one that was run by Time magazine which obviously has been darkened, and it makes OJ look a little bit more sinister. And there was a lot of people that complained that this really was a racist type thing that Time magazine had done. Now, whereas you could argue this particular one would be relatively easy, you could go out and get the booking photo. If these images were available and they were watermarked inside the camera, and by the way, police are very interested in using watermarking technologies when they acquire forensic images, it would be very easy to show that the image on the right had been manipulated. Okay? Now here's a good one. This is a good manipulation. This is the lady a couple of years ago, and maybe not quite that long ago. This is a lady in Iowa who had 7 kids, if you remember that. Okay? The image on the left, they were nice to her. If you look at the image on the right, she actually has broken front teeth. And the image on the left, they fixed her front teeth. Okay? So I guess why I put this here is that I want to tell you that maybe not all image manipulation is necessarily bad. Okay? But there's another example of some things. These things, magazine covers seem like it always, I guess the deal here is to get you to buy the magazine, right? So, now here's another one I like. This is an image that's very famous. It's available on the internet. And this is an image of taken, supposedly it was taken two summers ago, I guess. Was it 2 summers ago? When we had that, I forget what the official, the Viking, or the Mars Explorer, and the little thing that crawled around. Well, this was a picture that was taken that claimed that on the horizon, and I circled it in yellow there, you could see something flying on the horizon there. Okay? Now, this image it's been faked, okay? But there are certain websites you can go to that actually will purport that NASA's trying to suppress this image, okay? Now, one of the things you could do if these images were watermarked again, you could very easily localize the fact that there had been something added to that image, and obviously it was a fake. So like I said, I have an interest in faked images. Here's some other ones I put up. Obviously, the one on the left, Marilyn Monroe never really knew Abraham Lincoln, as far as I know. The one on the right is the actress Julia Roberts, and that is the president of North Korea. Okay? And I will tell you that the image on the right of Julia Roberts is triple faked. Okay? It's not Julia Roberts. It's Julia Roberts' head. It's her body, and it's somebody else's chest. Okay? All right. Now, if you look at cryptographic images as far as doing this for, issues as far as images are concerned, you basically can protect the image until decryption. And then once you decrypt it, you could make multiple copies of it, and there would be problems with, copy control and other things like that. If I then, decrypt an image and then I make multiple copies and start selling it, maybe the original user might want to know, who is taking his images and selling them. Okay? So we're big fans in our research group of also doing timestamping, because one of the things as far as copyright law is concerned is there's this issue, like most times, is who did something first. And a cryptographically strong third-party escrow timestamp will allow you to actually timestamp. This basically what you do is you essentially hash the data. You send a hash. I'm being very general now. You send a hash off to some third party that essentially signs it and then sends it back to you. Okay. Now, watermarking basically is the use of perceptually invisible authentication techniques is one way of looking at watermarking. And basically, as I said before, you take distortion, you introduce it in the data. Now, there are other forms of watermarking, for instance, visible watermarking. An example of visible watermarking, when you watch TV and you see the little CBS logo in the lower right-hand corner or something, that's obviously visible watermarking. There's been some other work going on in visible watermarking. For instance, there is a project, the Vatican put together a project on, it's called the Vatican Digital Library Project, where they essentially digitize a lot of the artwork of the Vatican Library, and they put it on a website in a university in Brazil. And those images all have visible watermarks. I mean, they're actually, you can't see the image without looking at the watermark. Now, some people say, well, that doesn't look very good. Well, the Vatican's attitude is, if you really want to see it, go to Rome. Okay? So you get a variation of it. Okay. If you look at watermarking, now here again, I should point out to you that watermarking is very interesting in the sense that it ties together a lot of things from security, but also it has an extremely strong signal processing bent. So I'm a little concerned that some of the things I'm going to talk about here, because of the audience, you may not, I hope it doesn't go over your head, and if you want to come back and ask questions later, and I'll try to do this as best I can. But basically, watermarking techniques can be broken up into 3 areas. There are, and this is for images, and I'll talk about video in a second. This would also apply to audio. You can talk about what is known as a spatial watermark. In other words, you embed that directly in the so-called spatial domain of the image. You could also take a frequency representation of the image. Typically what's done is you would do something called the discrete cosine transform, which is related to the discrete Fourier transform of the image, or you could also embed it in the wavelet domain. And there are applications of both of those that are very important, and I'll show you some. And then, of course, there are visible watermarks. Now, watermarks are characterized by essentially 3 components, and this diagram here shows it in a sense. You essentially have an original image. You then pass it through a watermarking algorithm, and you get a watermark image. So what you have here is you have some sort of a watermark structure that's defined, and we'll say a little bit about what that is. And that watermark structure somehow is tied to maybe the owner or some other type of thing. You have a marking algorithm essentially takes that watermark structure and embeds it into the image. And then you have a verification technique, and what that verification technique does is it verifies if the watermark is in the image. Now, from a signal processing point of view, this is kind of the classical signal detection problem. Most of these verification algorithms are basically signal detection algorithms. They're essentially, you can think of them as being binary hypothesis testing problems, and you can use all the various tools that come to bear from looking at signal detection theory as far as the verification algorithm is concerned. You can look at the watermarking problem itself as you're taking a structure and you're bedding it into the image, and what you'd like to be able to do is make sure that structure survives. So in a sense, you can think of the image as being a noise structure that's trying to interfere with the watermark, or even maybe somebody's trying to attack it's trying to interfere with the watermark. So this is a very similar to a communication signal where you're looking at a kind of signal and noise type problem. Now, the main principles of watermarks, particularly these invisible watermarks, this doesn't of course apply to the visible watermarks, is transparency. You would like the watermark to be not visible in the image under typical viewing conditions. Now that term, under typical viewing conditions, if it sounds like weasel words, it is. Okay? And it really depends upon the application. Because if I look at the image, let's say if I just look at the image from across the room, I may not be able to see the watermark. But let's say if I'm watermarking high resolution aerial reconnaissance images, and I put them on a light table and I look at them under magnification, I might see the watermark. So it really depends upon the application. The other one is robustness to attack. So the watermark can still be detected after the image has undergone certain types of linear and nonlinear operations. Okay? Now this may not be a good property. As a matter of fact, there are a class of watermarks. We certainly have developed a lot of them here, and we're actually patenting one here at Purdue. I should point out to you, I'm making money on watermarking, okay, which is unusual for me. I feel good about that. Okay? And that would be a fragile watermark. A fragile watermark would be one that would be easily attacked. Okay? There's the other issue of capacity, and this is more of a very interesting theoretical issue. In other words, how many watermarks can you stick in some sort of an image or structure such that you can independently verify each watermark? And this is really important because it's very possible that in the future when you buy a DVD player, it's going to have a re-watermarking section in it. When every time you play the DVD, it's going to re-watermark the output. Okay? So the question is capacity, how many you can put in there. This is a very interesting theoretical problem. It's an information theoretic problem that has a lot of interesting implications, okay, as far as looking at what you can do and what you can't do as far as watermarking is concerned. And we're greatly interested in these types of problems. Now the types of attacks that people have talked about is you insert the watermark into the image and maybe you compress it. Maybe you compress it using JPEG or a wavelet-based technique, or maybe use JPEG 2000, which is the new standard that's going to be coming out in another year. You could also do certain types of filtering on it, maybe do low-pass filtering or some sort of blurring or something like that. Some of these watermarks will actually survive taking the image, printing it, and then rescanning it. This is a so-called conversion back to analog. It's a printing rescanning attack. And I'll show you an example of a watermark that will survive that. There are also geometric attacks, such as cropping, resampling, rotation. And then there are collusion attacks where you get you get a copy of the image and you get a copy of the image, and they have two different watermarks in them, and you can use those to collude. And this is also can be done in certain cryptographic applications. You use those to collude to essentially try to remove the watermark or damage it or whatever. Okay. Now I mentioned fragile watermarks, and fragile watermarks are important. These are watermarks where the changes to the images can be easily detected and localized. So for instance, if you're a police force and you take images, digital pictures, and by the way, a lot of police forces do not want to take digital images because they're afraid the fact that there's more manipulation that can be done, although I don't really believe that. If you stuck a fragile watermark into the digital camera, and probably in another 3 or 4 years all digital cameras will have watermarks in them. If you stick a watermark into the digital camera, it's a fragile watermark, then if any changes happen to that, okay, and in forensics you're very interested in preserving the so-called chain of evidence. If any changes occur in those images, in those pixels, little changes, you can localize those and detect that it happened. Now you could also do this by hashing, and we've also been looking at developing image hash functions that will allow us to do this. That's one of the things that Ray has looked at over there for a while. We made a paper on that. So this can be used mainly for authentication and not copy protection. Copy protection, you're probably going to want to have a much more robust watermark. Now I mentioned that transparency is important as far as watermarking structures are concerned. There are several layers of transparency people talked about. You can do something simple like embed the watermark into essentially the low order bit planes of the pixels. Okay? Now you can make the mark be imperceptible, and you can actually use some models of essentially you can embed the watermark in areas of the image that you really don't notice very well. This is essentially exploiting things like spatial masking models, which essentially model your human visual system response. These watermarks have a tendency to be fragile watermarks, because if you just stick them in the low order bits, you can do things like dithering on the low order bits and probably not change the images that much, but you will destroy the watermark and essentially remove it. But that's okay if you think the watermark's supposed to be in there. A fragile watermark test would remove it. There are also things you could do in the transform domain where you just essentially add the watermark to the transform domain coefficients, and I'm going to show you an example of that. You can do transforms that are based on the human visual system models, and we'll say a little bit more about that. The thing that we're most excited about in our research group here at Purdue is looking at these image adaptive watermarks. We've been working on these image adaptive watermark problems now for about a year, right, Ray? A little bit longer than a year. About a year and a half with Bell Labs. We've been doing this with Bell Labs. And we're looking at several types of these watermarks, and I'll show you examples. We're actually going to be extending this to looking at video. Here what you essentially do is you exploit models of the human visual system. And what it boils down to is that you embed the watermark very strongly in areas that you cannot see. Okay? One of the things that maybe you don't know, but what you're looking at right now is not really the true irradiance function coming off the scene. Your eye is a low-pass filter, and some of the high spatial frequency content you're essentially suppressing, and you're suppressing other things. You can exploit things like edge busyness. I can stick things in edges that you won't be able to see because of the frequency response of your eye. So we're really interested in looking at these types of things over here. We're interested in particular, where's it at? We're interested in determining formal visual models and then adjusting the amplitude of the watermark. Now why do you want to do this? Well, the higher I introduce the amplitude of the watermark that I insert in the image, the easier it's going to be to protect. However, if I don't do this right, the higher I insert the amplitude into the watermark, the more likely it is you're going to be able to see it. So if I do this in a very careful way, a very nice, careful way, and I'll show you some examples of this, I'll be able to insert it in a relatively high amplitude so I'll be able to detect it and also prevent attacks, and at the same time you won't be able to see it. Okay? Let's talk about we'll talk about a simple watermarking technique. This is a fragile watermark. What you could do is you could generate a random binary sequence. In particular, what I'm talking about here is a bipolar M sequence. M sequences, maybe if you studied stream ciphers, I don't know if some of you have taken the cryptography class. I don't know in the CS cryptography class if you talk about stream ciphers. We have a cryptography class in EE that I've been teaching now for about 6 years. And in that class, we do talk about stream ciphers. In stream ciphers, you could talk about generating M sequences, which are basically binary sequences. They're pseudo-random binary sequences. They have really nice correlation properties. You could generate one of these things, and you could either generate what we call a bipolar sequence or a unipolar sequence. You can modify these essentially to fit one row of the image and then just add it to the image. Either you add this sequence, you add this sequence. Now you have to be careful. If you want this, let's say, to be an 8-bit grayscale image, you'd have to worry about clipping this so it doesn't go negative or above 255, for instance. So you can embed these row by row. What you do then, as far as the detection algorithm is concerned, what you do is you just form a simple little correlation test. And then you take this test statistic there and you threshold this test statistic by looking for peaks in this correlation. So in a sense, it's kind of a classical signal detection problem where you formulate this correlation model. Based on that correlation, you then test that. You do a hypothesis testing on that test statistic. Okay. Now, one of the things that's interesting here, let's go back to here. There's two other forms of watermark classes I didn't talk about. And that is, if it's necessary that you have the original unwatermarked image to test an image to see if the watermark is in it, that is what is known as a private watermark. If it's not necessary to have the original unwatermarked image to test an image to see if the watermark is in it, that's what is known as a public watermark. And this, by the way, is an example of a public watermark. We'll show you some other ones as we go along. I'm going to come back and talk about this in a second. Okay, let's take a simple one. This is a relatively simple one. I'm actually going to show you some images here. This is a so-called DCT Coefficient Modulation technique. And what you do here is you essentially take, for instance, let's say a bipolar binary sequence or a bunch of 0 and 1 unit variance Gaussian random numbers. And you take an image and you take the discrete cosine transform of the image. Now, if you don't know what the discrete cosine transform of the image, the discrete cosine transform is used in JPEG. It's also used in MPEG. It will not be used in the new JPEG 2000 standard that's coming out. But the discrete cosine transform, if you don't know what that means, just think of it as an image as being a big matrix of numbers, and what you do is you're taking a matrix transformation of that. And the discrete cosine transform has lots of interesting signal processing properties, and it's really good transform to take, and you could show under proper conditions that's theoretically optimal in a mean square sense. So what you do here is that this is the discrete cosine transform of the original image. So what you do is you scale those random numbers, you add it into the DCT domain, and then this gives you the essentially discrete cosine transform of the watermarked image, and then you do the inverse transformation and you get the image. So the verification, actually I'll come back to that. Here's an example of an original image. Okay, this is my stepdaughter Tia. Okay. Here's the watermark embedded into the image, and that weighting factor is 0.1. Okay. This, by the way, is a reasonably robust watermark. This watermark would survive printing and rescanning attacks. It would survive a lot of cropping and other types of attacks. What I'm going to do is I'm going to go back into this equation. You see this value for A? I'm going to slowly increase the value of A. And as I increase the value of A, you'll start seeing the watermark. So there, whoops, there it is once. Now I increased it. Maybe you didn't notice the difference, but I'll go back and forth. Look right here, right around Tia's arm. You see that little structure starts getting added there? Now what's interesting is we can immediately see the aspects of the human visual system here. Around the edges, you start seeing it down by Tia's knees and things like that. But that similar type of structure is also popped up in the bushes. Now if I rock back and forth, you can see it a little bit in the bushes. But the fact of the matter is, if I had showed you it a priori without telling you about it, you would have said those bushes were fine. So in a sense, that, even though this is not a full-blown human visual system watermark, it exploits that. So here it is. I'll start torquing it up a little bit more. Now these watermarks would be useless. I mean, I'm sure you want to go out and buy an image that looks like this, right? Okay. And there it is, torqued up even more. So you can see how the watermark is distributed through the image. Now this watermark is distributed in the spatial frequency content of the image. So to attack this watermark, you're not going to be able to get by with something simple like just, dithering the bits or something like that. This watermark is an extremely robust watermark, and it's related to a class of watermarks that are called spread spectrum watermarks. And I can't really get into that because that starts pushing off into some pretty theoretical issues. As far as how do you do the detection, what you essentially do is you invert this equation. You have Essentially, an image that you think has a watermark in it, you invert this equation, you then find the estimate of the watermark, you form this test statistic, and then you threshold this test statistic. If it's greater than some threshold, and there's all kinds of ways of doing the test statistic, and there's even ways of taking this test statistic and processing it. So like you could locally correlate this test statistic and not just do it on a pixel by pixel basis. Okay? Here's another watermark. This is a watermark that we developed here. This is called the variable two-dimensional technique, or VW2D. I can't go into a lot of details about why it's called that. It is a watermark that basically is tolerant to things like linear and nonlinear filtering and also JPEG compression. It also does localization. A variant of this watermark is a fragile watermark that we have developed, and there's some papers on our website about it. What it boils down to, again, is what you do is you form essentially a bunch of 8x8 blocks of random numbers, binary random numbers, and then essentially you tile these. I should point with this and not with my finger, right? So when I point like this, you all know what I'm pointing at, right? You could form these different W's that are tiled over the entire image, and then you essentially add those to the image. The technique, we've done a lot of studying. The test statistic here is a little bit different. We formed this test statistic delta. From that test statistic, then we were able to see whether or not the image is the watermark is in the image. This is what is known as a public watermark. You do not need the original unwatermarked image to be able to do it. This watermark is a little bit more fragile than the other one, but it has some really interesting applications. And a variant of this watermark has been patented by the Purdue Research Foundation, and we're making money on it. Okay, so here's an example of this is the watermark version of TIA, and that's the information that we embedded. Okay, and I guess we can embed, I don't know, what can we embed, Ray? I don't know, how many bits? Lots of bits. Several hundred bits. Yeah. I don't remember, I forget. Ray will tell you afterwards. Okay. Now we've done a lot of evaluation of this. We've done things like, there's some disadvantages as far as bit plane replacement, stuff like that. But we got localization, we can do JPEG compression to reasonable compression levels, and we can support multiple watermarks, which is important for our application. Now one of the things that we're doing a lot of work on now is looking at visual models. Now these have been developed extensively in the image compression business, and what these basically say, in a sense, is how much can you take one of these frequency domain transform coefficients and imperceptibly change them. Wiggle them a little bit, and you still can't see in the original image that I wiggled at. Okay? And this comes about by looking at results using psychovisual models and developing something what is known as the just noticeable difference, or sometimes called the JND. Now in the compression community, this is sometimes used for quantization step adjustment and some other parameters. It's also been used, I think, in some motion vector stuff in MPEG, hasn't it, Paul? I think it has. And we're using it here to look at some watermark amplitude variations. Here again, this equation's a little busy, but what it boils down to is this watermark, we insert the watermark basically by scaling it by the just noticeable difference, and we only insert it if the just noticeable difference is actually less than the transform coefficient. Otherwise we don't insert it. So it's a little bit different than just randomly inserting it in there. And we can do this both in the wavelet domain and in the DCT domain. Here's an example of, this was done in the DCT domain. What you see on the left-hand side is the watermarked image, and what you see on the right-hand side is what we embedded in there. And I don't know how good your monitor is. The one I got in front of me here really sucks. But if you look here, you'll see that we actually embed the watermark at different strengths depending upon where we think you'll notice it more than others. And this allows us to embed the watermark with a higher strength, and then from that higher strength it makes it easier to detect. Here's an example of another one, and if you could see it, I don't know, can you see much on the right-hand side? You can see stuff? Okay. You'll see that in the skin areas on the face, we don't put the watermark in very strongly. But we put the watermark in pretty strongly in the hair, because we can kind of mess your hair up a little bit and you're not going to notice it. Well, maybe some, well, never mind. I won't say that. Okay, here's another example of this. You notice in areas where there's reflection and things like that, we also don't embed the watermark as much. Okay? Now, we've done a very interesting study that we published in the 1998 International Conference on Image Processing, where we looked at the, you know, how do you, if you compress these so-called image adaptive watermarked images, what you should do. So if you're going to embed the watermark in the DCT domain, you probably should use classical JPEG. If you're going to watermark the image in the wavelet domain, you probably should use something like JPEG 2000 or the CZW technique. So mismatching domains can actually weaken the watermark, and that paper is available on our website. That was some stuff that Ray did. And at CI Polachuk, you see there is Christine Polachuk from Bell Labs. Now, one of the things that Fred Mintzer and his group and I credit Fred for getting us interested in this. I got interested in watermarking by having a conversation in a bar with Fred in San Jose, California in 1993. That's how we got into this. Fred's group proposed this so-called IBM re-watermarking attack. And here's how it works. So you have to follow the equations here. And these equations don't actually mean that this doesn't imply that this watermark is necessarily embedded in the spatial domain. Just think of this as I'm saying I'm inserting the watermark. Okay? So what I could do is I could take an original image X and an image and embed that watermark W1 in that, and I would get a watermarked image Y1. Now what you could do is you could take Y1. Let's say I take Y1 and I post on my website. So then you could take Y1, and what you do is you have another watermark, and essentially what you do is you subtract. Now either the subtraction means essentially you extract the watermark, a watermark, and then what happens is that Y1 now appears to be a marked version of XF. So the question is, who has the original? Is XF the original, or is X the original? So the way this works is that you could claim you have the original, and I stole it from you. Okay, this is a re-watermarking attack. Okay, and this was a real problem. And Fred Mitzer's group proposed this and a couple of other interesting attacks. Now, as I said, which one is the original, X or XF? The attacker could have claimed that XF is the original. Now, one way to get around this is to timestamp the original image. So for instance, if you then use the timestamp certificate as a way of generating the watermark, because a lot of these watermarks are generated using random number generators, you could use the timestamp certificate, let's say in a simple, crude way, in the seed of the random number generator, and essentially then the watermark itself depends upon the timestamp certificate. So essentially I got the timestamp certificate in a sense embedded in the image. And then all I got to do is you then re-watermark the image, then I say I have the original and I can prove it because I have my timestamp. You show me a timestamp that was generated from, quote, your original that predates mine. And they won't be able to do that. Okay? So we're really big on still using timestamping. This is probably the only way to get around the re-watermarking attack is to do timestamping. Okay. Now there are some, quote, anti-watermarking techniques around. The most popular one that's known the most is the stir mark. And we're we have very good relations with these guys, Fabian and his group at Cambridge. As I want to point out to you that maybe you have, read some stuff about watermarking and you think that stir mark removes the watermark, okay? Stir mark does not. I repeat, does not remove the watermark. What stir mark does is it can make your watermark detector not detect the watermark. But there have been some work that's been published, and we're working on some stuff here, using image restoration techniques where essentially you invert the stir mark attack, and then you can extract your watermark. So, and even Fabian's group at Cambridge, and I have a paper that he submitted to a watermarking conference that I'm the chair of, has actually proposed some techniques that actually get around his attacks. So some people say, oh, I can just stir mark and remove the watermark. Well, stir marking does not remove the watermark. And there are simple ways of actually post-processing the signal to essentially change your detection algorithm to be able to still detect the watermark. There are commercial systems. The most famous is Digimark. You can go to their website. They have lots of intellectual property. Digimark, we have very good relations with Digimark, and they've done a lot of interesting things. You can go out to their website and see the types of things they're doing. They're actually selling some watermarking technologies, and they're involved in some of these issues having to do with standards, which I'll say a little bit more about. We can talk about video watermarking, and here again, I don't know how much the audience understands about video and digital video problems, so I'll do it. And if we have some problems, we can talk about this maybe offline. You could use still image approaches. You know, a video is nothing more, let's say in the United States, is nothing more than 30 separate images per second. You know, the frame rate is 30 frames per second, at least for standard definition digital video. And you can play games with maybe there's different data rates at high definition television. If you're going to then take that and use the MPEG compression algorithm, there is a problem with how do you embed the watermark in these special types of frames that exist in MPEG, so-called B frames and P frames, and also the so-called motion vectors that are generated by the MPEG stream. Unfortunately, I can't go into details, and if you want to know more about that, I can talk to you afterwards. I know there's some signal processing students here that know what we're talking about here. You could also hash part of the compressed video stream, and people looked at using hashing approaches, and we actually have a video hashing technique that's in one of our patents, right? It's still in there. Yeah, it's still in there. Okay. That was the one that was put on national security hold or something. I don't know. So you can, there are techniques that will prevent things like multiple viewing, copying, editing, and doing inserts. And you can all do this with watermarking. Many of the watermarks will also survive conversion back to analog. In other words, you take the analog NTSC output, you take that output, and you redigitize it, and the watermark survives. As a matter of fact, there's an application where people are talking about taking movies now in a movie theater and digitally projecting them. There was a study that was done this summer where you could go see Star Wars using 2 different technologies. One way people go and pirate images is they go into the movie theater with a camcorder and they point it at the screen and they essentially make a copy of the image from the screen. Well, there's a watermarking technology that was developed by Qualcomm that essentially Ray worked on over there, my student this summer, that will prevent you from doing that. Essentially tags the sequence to the particular theater, and then if pirated copies come back, they can then exactly figure out where it came from. So there's been a lot of work in that area. Pardon me?
That's the goal.
That's the goal. But actually, it does reasonably well. Okay. You cannot trivially extend watermarking techniques to video. Because there are things like other attacks, particularly things like collusion, frame shuffling, you can do insertion, and they can be computationally expensive. Okay, so sometimes you have to worry about that. You could do things like you could mark each frame with an independent watermark, and then you have to worry about things like colluding across frames. You could mark each frame with the same watermark, but then you could do scene change detection where you essentially, when the scene changes, you essentially assert a different watermark, and there are actually trade-offs between both of these. One of the things that we're looking at is looking at scene-based watermarking. We're doing a lot of work in that area. As a matter of fact, Steve, can you go ahead and show that video now? Here's an example of image. Well, it's not moving yet. Is it going to move, say, Steve? Here we go.
Yeah.
All right. Okay. Yeah. Okay. We'll wait. So what you see on the left-hand side is an original image, and what you see on the right-hand side is something that's been video watermarked. And you can't see the watermark in there. But that watermark could be used then to identify the image. That watermark could also be used for copy control. So copy control information could be embedded in there. So for instance, there's a move to, I'll say a little bit more when we get there, but there's a move to maybe flag certain images being never copied. So that would prevent you from actually copying this thing in a sense. And other ways around it. I'll say more about that as we get there. But what you're seeing there is this is a test sequence. This test sequence has a name. It's called the traveling salesman sequence. I don't quite really know why. I think that guy's trying to sell that thing, whatever he's holding up his hand. What is that? Some sort of explosive device or something? I don't know. Maybe it's a pipe bomb or something. So. All right, we can go back here, Steve. Here again, this is something that's very MPEG-oriented. Maybe I won't do it because it involves actually understanding how the MPEG bitstream works. But the whole point of this is when you watermark video, there's been a lot of work at either watermarking video in the uncompressed domain or watermarking it directly in the compressed domain. I think what I'll do is I'll skip ahead a little bit. There's been a lot of work in data hiding. We have some people in our group looking at data hiding, the idea of embedding a second stream into some sort of host file. And people looked at this for all kinds of applications, some of which have nothing to do with security. For instance, there's been some work done. If you look at image or video databases, there's metadata that you extract about these images. And one of the questions is how do you bind this metadata to the actual original image or video? And people are looking at watermarking technologies to bind the metadata to the images. People have done that. People have looked at doing picture-in-a-picture. We saw an example of a video of the Boston Philharmonic that had a Madonna music video embedded in it. And you could watch the Philharmonic thing and no problem at all. If you were able to extract the other one, you could get out the Madonna video. Okay, and we're actually looking at some things in data hiding. One of the questions you want to ask is, what's the capacity problem here? How much data can you theoretically hide into an image or a video? Now, there's a lot of standards going on, and one of the things that's going on, one group that's very active in the United States is something called the Data Hiding Subgroup of the Copy Protection Technical Working Group. And the last group there, the CPTWD, is pronounced CP-TWIX. Okay? The CP-TWIX has been meeting once a month in Burbank for the last 41 months. And what they're doing is they're proposing standards for keeping honest people honest. Okay? It's very controversial. The goal here is to protect DVD content. Next generation DVDs are going to be both watermarked and encrypted. Okay, so it will be difficult, relatively difficult, for people to get access to the bit stream. Now, does that mean it can't be hacked? You know, of course it can be hacked, but they're going to have some problems associated with it. The CP-TWIX, their goal, in a sense, I have to be careful what I say here, but one of their goals, some of you maybe know about copyright law, there's this concept of what is known as fair use. In other words, you get to make a copy for fair use. That is a permission, in a sense, that is given to you by the law. It's not an obligation provided by the copyright owner. So in other words, if the copyright owner can prevent you from exercising fair use, it's still legal. In other words, if they can prevent you from making copies, it still is legal as far as the copyright law is concerned. Yeah?
Tested in the courts?
Yes. Yeah. And the people that own content in Hollywood want to prevent you, unless you get their permissions and pay money, on making copies, even fair use copies. Okay? So some of the content will have flags like copy never, copy once, copy no more. Okay? And this is a very complicated thing. The other thing I would tell you is this standard is not an open standard. It will not be released to the public. Oh, you can get access to it if you want to pay like a $500,000 bond. The guy in the white there, I bet you have that. You look like you're a rich guy, so I don't know. There's also a group in Europe called DAVIC, the Digital Audio Visual Council, and they've been pretty active too. And this is part of the European Union. So they don't always meet in Brussels, but they meet in Europe, and they've been active. A similar type of thing as far as protecting content is going to occur in Europe. There's been some work done in looking at video security. In particular, you could do things like naive encryption, where you essentially encrypt all of the video stream. And that's going to be done, by the way, in the next generation DVDs. They're going to be using triple DES as the encryption algorithm, or they might use some aspects of the AES, the Advanced Encryption Standard, once that gets done. It's still not done yet. There's also been some work at selectively encrypting parts of the sequence. One example of this was the recently failed DivX system. I know some of you know about DivX, okay? Now, a lot of you out there think maybe DivX failed, okay, because a lot of people on the net said, oh, we don't want this, blah, 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 it's against the rules, all that stuff. No, that's not why DivX failed. Every time I hear that, I think of a bunch of lawyers back in Burbank that are laughing at you, okay? The reason why DivX failed was because the Motion Picture Association of America, many of their members decided not to provide content to DivX. Why did they not provide content to DivX? Because they're more interested in what's going to come out of the CP-TWIX. So they didn't care about anything to do with the fact that people were trying to strike a blow for net freedom. Average consumers didn't buy the players because there was no content that was available for the players, not because they were striking some great blow for intellectual freedom. Okay, and there was no content. There was very little content that was available. So I think DivX is very interesting. It was actually a very nice system. It had a lot of interesting features in it that are going to be incorporated into CP-Twix. It did partial encryption using triple DES of the bit stream, and it also used watermarking for a combination of those. Oh, here's just some systems you could look at. There's a system in Germany called Syscop. It's a very kind of interesting thing. It's a web-based image security system. Allows you to kind of register, and you can essentially register individual images, and you can watermark them, and you can actually then sell images via the web. You can take a look at that URL if you're interested. So one of the things that's interesting about Syscop is they developed this thing called the TIE toolkit, which stands for Tool for Image Encryption. It's kind of neat. It also uses watermarking, but one of the things it allows you to do, and it will dovetail off of some of the stuff that's going on in the JPEG 2000, what it does is it partially encrypts some parts of the image content. So in one incantation of it, it will allow you to look at a low resolution version of the image, where the higher resolutions are essentially encrypted. Okay, so it's kind of an interesting approach, and it's consistent with what's going on in things like JPEG 2000. There's another company here called Intellectual Protocols 2, and they're all actually looking at a product called CopySite, and this is a complete set of web tools for watermarking and protecting intellectual property rights. I have to put a caveat here. This is the company that we are working with, and this is the company that has bought rights to our algorithms. Those watermarks they're talking about there were the ones that were developed here at Purdue. Okay. Now, here's some controversial things. This is based on the presentation I gave at the ACM Multimedia Workshop in Brussels, England last year. It is true watermarking technologies have not been tested in court. I'm sure Gene will tell you trying to get a judge to understand encryption is not easy. Trying to get them to understand watermarking is not going to be easy either. I feel that watermarking probably, encryption has been around for a long time, and it's now being used. I mean, it's been used for a while, and there's some pretty good successful models for it. Watermarking of images and video have only really been around for about 5 to 7 years, depending upon how you count. I feel that the technology is too immature to actually be putting it in products at this time. In some cases, when you initially explain it to people, particularly lawyers, they love it, okay? And my concern is that it's too much right now of feel-good technology. There's a lot of theoretical problems we don't know the solutions to, okay? Particularly for some of these embedding technologies. I mean, I can propose some solutions, but I think it's not obvious to me that the technology is mature enough yet. That doesn't mean I'm going to stop working in it, because I think it's a fascinating problem. In some applications, you might be better off just doing timestamping or other forms of authentication to protect your content. As a matter of fact, as I mentioned to you, I'm a big fan of that. I believe if you have content, you should timestamp it, okay? Now, the other question is, the watermarking testing techniques are based on statistical tests. How do you prove to a judge when you say that your watermarking technology survives some sort of attack based on a statistical test, that that's valid? We know, just talking about statistical things with the DNA evidence in the OJ trial, how much that did not convince a jury. I think it's going to be a problem, okay? I think image encryption or video encryption will have limited uses in what I would call the large transmission channels, but not on link systems that you'll have in your house. So I think you'll see, it's definitely you're going to see that DVDs and other things like that are being encrypted. But I think people will try to use other things like watermarking and maybe timestamping to protect their content a little bit more. There is this Digital Millennium Copyright Act. I don't know if Gene has talked about that much. One of the things that the Digital Millennium Copyright Act says that if you deliberately circumvent features that somebody put in their content to protect it from copying, that you violated this act. And there is some debates going on about whether or not that violation will be a civil penalty or that violation will be a criminal penalty. Okay? I know that there are some U.S. attorneys. I attended a meeting in Washington last March, and there are some U.S. attorneys that want that penalty to be a criminal penalty, which makes it a whole different game. Okay? And a lot of people that own content want it to be a criminal penalty. I don't want it to be a criminal penalty, but I'm sure they're not going to ask me for the final opinion. Okay. Okay. Here's some conclusions. I believe the secure multimedia system is evolving. I think simple add-ons, like just encrypting something somewhere, will not work. I think you need to have techniques that exploit the unique nature of the data and the fact that in many ways this is sensory data. This is data you're going to look at, or this is data that you're going to listen. That gives you a lot more leeway than a document or an email, because I can screw it up a little bit and you won't notice it. Okay? I can distort it a little bit and you won't notice it. Now, I'm sure all of you got golden ears and golden eyes out there, but most of us don't, particularly these 50-year-old ears. Okay? I think watermarking will be crucial to the secure network multimedia system, but not now. I think there's a lot more work needs to be done. I think timestamping is important, but it's been largely ignored by the multimedia community and the watermarking community. Okay? And I think unique things that are going to be tolerant to changes, particularly things that are compatible with compression. Okay? If you want to see a good paper, even if I say so myself, there's an excellent review article on perceptual watermarks for digital video and images that appeared in the proceedings of the IEEE. 1999. It was published by myself, Chris Polachuk at Bell Labs, and Ray Wolfgang, who's sitting over there, is one of my Ph.D. students. And you can get a copy of that paper at our FTP site there. You can just go to my webpage and you can find copies of that. We're going to hold the second conference on security and watermarking and multimedia contents. This is going to be in January of 2000 in San Jose. There's a website to describe you more about it. Last year we had about 60 papers in that workshop or conference, and this year we're going to have about 75 papers. And we're going to have papers, I think, this year from about 25 different countries looking at security issues and watermarking. And we're going to have some presentations from the consumer electronics companies talking about how they're trying to use security features and for things like copy protection and content access. There is a watermarking resource. This is an extremely long URL. You can get access to this from our watermarking webpage at Purdue here. This is a watermarking resource that's maintained by Frank Hartang, who was at the University of Nuremberg-Erlanger, although Frank now is graduating, is at Ericsson, but I think he's still maintaining his webpage. There's a lot of neat stuff there. I think it is 5:30, and I think I will stop here, and I'd be more than happy to entertain questions if you have any questions. Anybody have any questions?
Where's your research going in the next 2 years?
Well, what we're mainly going to be concentrating on is looking at these scene adaptive techniques, particularly that are more robust to attack. So we're doing a lot of work in that area. We're also we're going to be looking at so-called geometry attacks, and we're also going to be doing a lot of work in looking at capacity issues. So there's actually some theoretical work we're going to do. Yes, sir.
What are you guys doing as far as with the MP3?
MP3. Oh, that's a really good question. Okay. Let me jokingly give you the sarcastic answer first, if you don't mind. My group, which is the Video and Image Processing Laboratory here at Purdue, we're pixel pushers. So we push pixels. So we don't do a lot in audio, although we're very familiar with what's going on with the Secure Digital Music Initiative, the SDMI. The SDMI will have 2 watermarks embedded in it. Okay. I don't know. I think, well, number one, you probably know this, the record music business is running scared. Okay. I think it may be too late. Okay. You still will be able to do the following. You will be able to take content and play it, and if your ears can tolerate it, which most people can, take the analog output, redigitize it, and then do anything you want with it. Okay. There'll be SDMI players that will be available this Christmas. They'll be using version 1 of SDMI. There'll be a version 2. The watermark in those cases are embedded using something called, help me out, not wavelets, but the other stuff. It's using a wavelet type of transform. It's going to be embedded in areas that are perceptually inaudible. Do I think it's going to work? I don't know.
Cepstral method or something?
No, it's a conceptual-based system. But so yeah, I think that you're going to see that's happening. There's an issue of whether or not in the future you'll be able to buy a player. You know, one of these handheld things. I have a Diamond Rio. I think they're really neat. Whether or not you'll be able to buy a player that will play both open content, in other words, content that doesn't have the security features in it, and players that play SDMI content. That's still out yet. And you can go, if you're interested, afterwards I can give you a URL where you can go get some information about the SDMI if you're interested.
Because there was a big, huge article I was reading about about a month ago.
Yeah.
The music industry. The only reason why a lot of the MP3 players are starting to hit the market is because the music industry is now starting to adopt the MP3 standard because they have no choice.
No, I think the music industry wants to adopt the SDMI standard, which is not MP3. It's a different type of compliance. Now, how secure is it going to be? I don't really know. I mean, I'm familiar with the technology. I can't tell you everything in the technology because I signed a non-disclosure agreement. But I don't know. I really don't know. But if the music industry has its way, everything produced in the future, at least digital music you can buy, will be SDMI compliant. And whether or not you'll be able to then create content that's SDMI compliant, play content that's not SDMI compliant on your SDMI player, nobody knows at this point in time. I think it's going to be a real problem. Okay, I really do. And that's also driving some of this work that's going on in video right now. So, is there any other question? Any other questions? Okay. I guess that's it. I'm not really sure who's going to speak next week, but I'm sure they're great. Okay? So thanks for attending. Take care.